Worksheets up front if you haven't gotten one already. That's how you're getting credit for attending class today. While you guys are getting settled, I'd like to introduce our guest speaker for today. This is Professor Gabriel Robbins. He is a professor in the CS department here at UVA. He's been here since 1992. His research area is nominally in all things algorithms. So he's got a lot of broad research interests in there. That spans through like how do you set up processors well, like where do you place your transistors when you're trying to design a processor in order to make your processor as efficient as it could be, all the way to bioinformatics algorithms that maybe hopefully one day could help people be more likely to cure cancer. So please give a round of applause to Gabe Robbins. And I'll turn the floor to him.
Thank you. Nathan asked me to give you a brief history of computing in a couple of lectures. It's a tall order because you can talk for many semesters about this stuff. And in the theory class, we go into a deeper kind of dive into this. But I'll try to give you in a couple of lectures a history of how we got from abacus to iPhone over a 2,300-year period. So here we go, historical perspectives. So first, why do we care about the history? Mainly because to see where we're going, it's good to see where we've been in many aspects of life. And the simplest ideas are often the most subtle and fundamental and important. It's good to know the big picture, the long arc, and you can see connections between ideas of different scientists and engineers and philosophers over the centuries and millennia in this case. The field of computer science has many parents. We'll introduce you to a couple of dozen of them today in the next lecture. And it's kind of inspiring to see what great minds do, how they think, what they achieve. It's also fun, so never underestimate that. So we're going to kind of stand on the shoulders of giants, as it were, to paraphrase Isaac Newton. And here are some of the luminaries that we'll cover. Not quite all of them, but the ones that circled in red are particularly significant to computer science and engineering and science in general, and of course math. And so we'll cover these people, and we'll see how far we can get. So everything starts with the ancient Greeks. Not all of history, of course, but the scientific revolution, the scientific method, the scientific thinking, the idea that it's good to put things to the test, not just believe them arbitrarily because somebody said so, but see how they hold water, whether they're consistent with other things. And so Aristotle is one of the first people that said that it's good to think and investigate and understand the universe around us using the so-called scientific method. He was the student of Plato and also the tutor of Alexander the Great, which is pretty cool to have your private tutor be Aristotle. And many things are named after him, Aristotelian kind of thinking and approaches. We already mentioned he pioneered the scientific method, and one of the most influential people ever. He dabbled in almost every field that there was. He's said to be the last known person to know everything there was to know in his own lifetime. That's kind of impressive. Of course, today we have a lot more knowledge than back then, but still. And Bernard Russell famously said that even if you want to debunk or challenge Aristotle on some things, you still have to mention him. So either way, he gets mentioned and cited and credited one way or the other. So he gets a lot of street cred for the stuff that he's done. In Cabell Hall, there's his famous painting, School of Athens, where Aristotle and his teacher Plato are prominently featured in the center, and many other luminaries are featured there too. For example, down here you can see Euclid doing some straight edge and compass constructions, and it'd be kind of interesting to kind of go through and see who else you can identify from historical figures in this painting. This painting was famously painted in the Sistine Chapel by Raphael, not the Ninja Turtle Raphael, but the actual Renaissance painter. So Aristotle gets a huge moon crater named after him. So do many of these people, and the bigger the impact on science and engineering and humanity, the bigger the impact crater named after him. His is 87 kilometers wide. So it's not to say that Aristotle got everything right, or the ancient Greeks in general. They thought that The periodic table had 4 things in it: air, water, fire, and earth. That didn't get them very far in chemistry, and therefore in biology or medicine it sits on top of chemistry, but still, at least that's some hypothesis that can be tested, and that's the crux of the scientific method. So Euclid, basically history's first serious geometer, pioneered the axiomatic method, which basically sits on top of the scientific method. You have a series of axioms, and in these axioms, you write a few things that you think are true and relatively obvious, and based on that, you come up with other consequences of these axioms, and you call them lemmas and theorems and corollaries, and you can do an entire mathematics over these axioms, and we do, and we have. And this book Elements is the oldest, most impactful textbooks ever written. It's had like over 2,000 editions over the last 2,300 years. It unified math and logic, and it reduced rigor to mathematical thinking. And it influenced every other famous thinker that came after that, including Kepler and Galileo and Newton and Einstein and many, many others. Right? So he too gets a lot of street cred for laying down the foundation for how we do math and science and engineering today. And it's still, after all these millennia, still the best method we know of how to understand the universe around us, how to be effective engineers and scientists and inventors and masters of technology, for better or worse. Euclid is also famous for his straight edge and compass constructions. Here are a few of these constructions kind of animated. For example, this one bisects a segment using a compass and straight edge. And kind of for fun, you can try to figure out offline what are the other ones doing. Here are the Platonic solids. There's 5 of them in 3 dimensions, more in higher dimensions. And here are Euclid's axioms. If you've never seen them before, now you've seen them. There's only 5. And from that, all of Euclidean geometry arises. The interesting one is the parallel postulate. And people question over the millennia whether that could be proven from the other 4 postulates. In fact, the first 28 propositions of his Elements treatise are based only on the first 4 axioms and not involve the 5th. And so people thought maybe you can do all of Euclidean geometry using the first 4. And only 2,000 years later, in the 1800s, did somebody show that it's independent of the other axioms, the parallel postulate. And independence of the axioms is a very interesting, weird situation. It means you can either decide it's true or false, whichever way you like, and then stick to it consistently, and the system will not become inconsistent, assuming it was consistent before. So based on these attempts to try to prove or disprove the parallel postulate, we obtained several other geometries that are non-Euclidean, including spherical and hyperbolic geometries back in the 1800s, late 1800s. And many books have been written about these topics. It's a very prolific area of mathematics, non-Euclidean geometry. I'm just showing you a few of the books. There's probably thousands of these books by now. And non-Euclidean geometry gives rise to all sorts of interesting manifolds, such as Klein bottles, Mobius strips, and projective planes. And these are just the 3-dimensional or 2-dimensional ones embedded in 3D. And there's many higher dimensional variations of these. You get very interesting, cool objects to study with peculiar properties. In spherical geometry, geometry is constrained to the sphere instead of a plane, and you get various interesting properties here. Oh, by the way, all these slides will be available online, so you don't have to follow every single nuance of it. You can look at them at your leisure. I'm going very fast here. Hyperbolic geometry, the geometry is constrained to kind of saddle-type surfaces, as the ones you see here. The work of Gödel, the work of Escher, the artist, is based on typically non-Euclidean hyperbolic geometry, where he did the angels and demons and other famous etchings of art. How many seen his work over time? The Escher kind of etchings. So he's based on this geometry. And these geometries, at the time they were invented, were thought to be kind of toy geometries, kind of mathematical musings. It turns out that the universe has hyperbolic geometry, as Einstein very powerfully demonstrated in his theory of relativity, when he used hyperbolic geometry to produce the theory of space-time and mass is equal to matter via the famous equation E is equal to mc squared. It's not based on Euclidean geometry, and in fact, the universe is not Euclidean. We didn't know that for all these millennia. Only in the early 1900s, when Einstein published his general theory of relativity almost a century ago, did we realize that the universe is not Euclidean. It looks Euclidean on a small scale, like this room or even this planet, but globally it's not. And if not for this kind of geometry, relativity wouldn't exist. If not for relativity, we wouldn't know that mass and energy are interchangeable through E is equal to mc squared. And if not for that, we wouldn't have nuclear weapons. And if not for that, World War II could have gone very differently. And the entire history of the human race was affected by non-Euclidean geometry, which in turn was just tweaking the fifth axiom of Euclid, the parallel postulate. So I want you to know it's not just some mathematical abstractions and exercise in intellectual curiosity. These things affected human history very, very dramatically. Millions of people lived and died based on consequences of exactly what I'm showing you now, going all the way back to the ancient Greeks. So it's quite dramatic, actually. I'll skip to some of the cartoons. I'll use them to encourage you to look at the slides offline. Eratosthenes, another Greek contemporary of Euclid, was the chief librarian of the Library of Alexandria. At the time, the Library of Alexandria was sort of the Google of the day. It had millions of manuscripts and parchments and clay tablets. Knowledge was literally chiseled in stone back in the day. Now we use that kind of metaphorically, but then it was actually the case. So books were expensive and only a few people had access to them. In fact, only a few people can even read. And when the Library of Alexandria burnt down, ransacked by invading soldiers, it was a huge loss to humanity. And much of humanity's knowledge was lost on that day when this happened. He famously measured the Earth's size to within 1% accuracy. And he came up with the earliest algorithm that we know of called the sieve of Eratosthenes, where you compute prime numbers by consecutively eliminating all multiples of integers and only the primes remain there. Oh, also he wrote on every subject that there was and had the idea of chronicling ancient history, and that means just writing stuff down. He invented written history, the notion that when something happens, you observe it and you write it down. I know it sounds almost silly to say that, like what else would you do when something significant happened? But people didn't do that. And that's why we don't know much about ancient history other than the really major things, like Alexander the Great taking over the known world when he was 27. But other than that, other than these major things, we don't know much about them. In 1,000 years, people will know almost everything about you, including what you had for lunch yesterday, because you posted it on Facebook, and it's all going to the cloud, and everything is backed up. And unless it's some major catastrophic event, like a meteor strike on the Earth, all this stuff will be recorded. And that's good, I guess. I don't know if you want people 1,000 years from now to know everything you tweeted and wrote and corresponded with today, but they will. Anyway, Eratosthenes had this idea of systematically recording things down, and of course we've done it since, and that's how we got written history. So here's the sieve of Eratosthenes kind of implemented graphically to compute primes. Here's how he discovered that the Earth's circumference is what he thought it would be in terms of miles. I guess in those days it was strata. So think about it. He knew that the Earth was round. Not only that, he calculated circumference. When other people later on said that the Earth was round, 1,000 years later, they were burned at the stake for saying that even. So even that knowledge that the Earth is a sphere rather than a flat plane was lost to history after the Greeks for many centuries, many steps backwards. And he gets his own moon crater, of course, named after him. The Greeks actually created an ancient computer called the Antikythera, and it looked like a Swiss watch. It had gears and intricate parts that turned and revolved, and it was quite sophisticated for the time. This is 100 BC, 150 BC. We just discovered this pretty recently. Right? Only a few decades ago did we discover this in some ancient underwater excavation, but this is a 2,000-year-old plus computer. We didn't know that ones existed that long ago. How many of you knew about this kind of computer from 2000? Good for you, but the human race had no idea. We thought that, Babbage's computer was one of the earliest ones, and maybe Pascal's handheld calculator from the 1700s. But this is almost 2,000 years earlier. Again, all that knowledge was lost due to political and religious upheavals and so on. Imagine if this was preserved through the centuries and people kept building on this, we would have had iPhones 1,000 years ago. And by now we probably would have, been colonizing the planets of the solar system, the moons of the solar system, and cured cancer and all sorts of stuff. So there was a lot of setbacks. But I digress. Here are some more parts of this computer. Again, these are replica, handcrafted replica based on the parts that were discovered. Some of the parts that were discovered, you can see here, they're almost kind of fossilized in rock, but still pretty recognizable. using X-rays and tomography and other techniques. And it kind of looked like that. He computed the motions of planets and moons and eclipses and so on. So that was pretty good. This is a Scientific American article on my website that tells you in just a few pages, some diagrams, how this thing worked and its significance and what it took to have constructed that 2,000 years ago. So I urge you to dive deeper into any of these topics. So fast forward 1,000 years to the year roughly 950 to 1050. There was this guy called Abu Ali al-Hasan ibn al-Haytham. How many heard of him? Okay, in Western cultures, he's kind of an unknown, but in Eastern cultures, he's a big hero, or he's also a hero to us, those that know of him. He was called the physicist. He wasn't called a physicist because there was only one physicist on the planet, and he was it, so he was the physicist. And basically one of the greatest minds of all time, certainly the greatest scientist of the Middle Ages. Contributed to every subject that there was, pioneered further the scientific method based on what Aristotle laid down, wrote treatises on optics, and he was a polymath. He authored over 200 different volumes, treatises on lots of different subjects, and he influenced Da Vinci, Descartes, Kepler, Galileo, Newton, and everybody else. This guy was their hero. I mean, we think of Galileo and Newton and Kepler as our heroes, but this guy was their hero. So he's like a hero squared, if you will. In some countries, he appears on the money. Other countries, people don't hear much of him, sadly. But that's kind of, cultural differences. For example, in the old days, people thought that in order to see, light emanates from your eyes, hits some object, and that's how you see it. That's kind of depicted in these etchings here. He said, no, light has to come from the object into your eyes, and that's how you see. I know it sounds obvious now when you say it. How else would you see? But, and also if light comes from your eyes to hit objects, and that's how you see, it kind of begs the question of why can't you see in the dark then, right? But people didn't think that way. They said, okay, we'll go with that. They kind of, that's what happens when you sidestep the scientific method and rational thinking. Happens a lot these days in politics. But I digress again. And he gets a big moon crater named after him as well for all that. Leonardo of Pisa, otherwise known as Fibonacci, he did a lot of stuff, including coming up with Fibonacci numbers and establishing the importance and ubiquity of the golden ratio in many aspects of mathematics. But most importantly, he basically popularized the Arabic numerals, the Hindu Arabic numerals in the West. He went to the Middle East and to the East and kind of saw how people count over there. And they didn't count like we did, like Greek numerals or Roman numerals. Try to take the square root of VM, DCL, X, VI. Good luck to you with that. You can't do math very well on Roman numerals. And if you can't do math very well, the engineering that sits on top of the math is hobbled, and so is any science that you try to do on top of the math, and everything gets retarded and is harder and more tedious, and you can't advance very far. If you have a good way to number things and to count, like these Arabic numerals that we now just call European decimal system, which we really copied from the Hindus and the Arabs, if you do that, you can count, you can do math and arithmetic, and therefore all the other higher maths on top of that much more easily, with great facility, more efficiently, and everything just flourishes and blossoms. So that's one of his main contributions. He did many other things, right? There's an entire journal devoted to the Fibonacci kind of types of mathematics that are associated with him, and Fibonacci numbers and the golden ratio appear in engineering, in architecture, in astronomy, even in galaxies, all the way down to flowers and sunflowers and famous paintings all involve kind of golden ratios and Fibonacci numbers. There's even Fibonacci number trading on Wall Street. How many heard of that? So there's lots and lots of applications of his work. Very impactful stuff. All right, René Descartes, 1500s, 1600s. He was the father of modern philosophy. Famously invented Cartesian coordinates that are named after him. Descartes, Cartesian. And that enabled to tie geometry to algebra via the coordinate system. And also it helps you place yourself on the map. Today using GPS coordinates or just latitude and longitude more generally. So he came up with that kind of way of coordinates that precisely tell you where every location is in a plane or in a sphere or any other manifold. He discovered momentum conservation principle and famously said, cogito ergo sum, I think therefore I am, which kind of gave rise to all of existential philosophy. and wrote some famous treatises on logic and math. He famously said, it's not good enough to have a good mind, you must use it well on top of that. So again, he furthered the scientific method and the scientific revolution. He gets a lot of street cred. He appeared under French francs before they changed to euros. Money was more interesting looking before the euro, kind of bland euro, came into being. They had to make a lot of compromises so nobody gets upset. That's a whole different story unto itself. So he had quite an influence. Fermat, one of his contemporaries, the father of modern number theory. Number theory was already investigated by the Greeks 2,000 years before, but he put it in a more rigorous setting and expanded it, and famously came up with his so-called Fermat's last conjecture, which later became Fermat's last theorem when Andrew Wiles proved it in the affirmative in 1993, roughly after 3.5 centuries of it remaining open. And the significance of his theorem, which here appears on a stamp, and the name of Wiles is there as making the equality unequal, so it's a nice little cutesy stamp depicting the theorem. One of the important significance of that is that it gave rise to dozens and dozens of other fields of mathematics, sub-areas of mathematics, in attempts to solve this. So it wasn't just the theorem that was the crux of it. It was the attempts to solve the theorem over 3.5 centuries. Thousands of mathematicians tried, mostly failed, but in their failure, they still devised brand new ways of proving things, entire new sub-areas of math. So he basically helped math blossom. He also influenced Newton and Leibniz and many others. He was also a physicist as well as a mathematician. And here are some books on Fermat's last theorem and the influence it had on humanity. And here's Andrew Wiles in 1993, after having proven it, smiling, as he has very good reason to, after solving a 3.5 century old open problem. And that's Fermat. Even the Simpsons episodes sometimes have cute little mathematical jokes in them. And here we have something to the 12 plus something to the 12 is equal to something to the 12. How many say that's really an equality here? How many say that's an equality? How many say it can't be an equality? It's false. Yeah, why? Well, it contradicts Fermat's last theorem, right? The exponent is 12, but this is a Fermat near miss. It's almost equal. If you work out the numbers, you see that they're very, very close. And there's a whole study of Fermat's near misses, and it goes on and on. So big influence. He gets his own moon crater, of course, and there's even a stage play called Fermat's Last Tango by the New York Theater Company. I've seen it on DVD, actually. It's quite amusing. It features Carl Friedrich Gauss as characters, and also Pythagoras, Pierre Fermat, of course, himself, Daniel Keene, Euclid, and of course Sir Isaac Newton. What could be better than that, to have a stage play with all these characters in it? If you get a chance and you get into a geeky mood, you maybe check that out. Pascal, mathematician, philosopher, physicist, came up with so-called Pascal's triangle, and that also he started to systematically study probability and statistics. What do you think the motivation for studying probability was back in the 1600s? Take a wild guess. Gambling, yeah. People were gambling for thousands of years, but couldn't get an analytical handle on it. And the human mind is very bad at probabilities and statistics kind of thinking. So he put it on a firm footing, mathematical footing, and started studying systematically, which is a great contribution, because now statistics almost everywhere you look. In every other field, we use statistics for all sorts of things, and he sort of pioneered that. So we owe him a lot. Even computers work in some statistical way, right? Errors can occur, bits can flip inadvertently, and you have to have some probability and statistics handle on how to construct a machine made of millions and even billions of parts, none of which are completely reliable, but together they must form a very reliable machine. And there's a lot of probability and statistics involved in building it, in running it, in proof testing it, and also eliminating noise and errors and glitches as they occur, right? Using error correcting codes and all sorts of techniques that are statistical and probabilistic in nature to increase the reliability of the overall machine. So it's everywhere, and we owe him this, the initialization of that study, which flourished to a tremendous degree. He also studied humor and wit and paradoxes, and he invented the world's first bus. I don't mean computer bus, I mean the actual bus that 50 people get on, and economy of scale in transportation. At the time, it wasn't so obvious, right? And there's standard international unit of measure named after him, the Pascal, and so is the Newton, and so is many other measures, the Gauss, right? The ohm, the ampere. So when you have an international unit of measurement named after you, you probably achieved something, because then your name is spelled with a little small letter, not a capital letter anymore, and that's actually a great honor. He also importantly constructed this little device. It's a handheld calculator. Remember, this is the 1600s. 1700s. So he had like a mechanical handheld calculator. Of course, at the time, this was very expensive. It probably set you back several years' worth of average salary, and all he can do is add and subtract, multiply relatively small numbers of 3 or 4 digits. But at the time, it was an amazing advance, because it could be done much faster than a human can, and certainly much more accurately. So he has one of the first earliest computers. Of course, we talked about the Greek Antikythera of 150 BC, but this was a more general device. So again, he gets a lot of credit for doing all that. And that brings us to one of the giants, Sir Isaac Newton. He wrote Principia Mathematica, which basically revolutionized physics and founded modern physics. And he also, as a sideline, invented calculus in order to do physics better, and put forward the theory of gravitation. Gravitation attracts as the inverse square law. That's due to him. And that, of course, enabled a great many other things, including moonshots and space travel and many other physics. He discovered the laws of inertia, the laws of motions. Newtonian fluids are named after him. Newtonian universe, kind of deterministic universe, cause and effect kind of thing. And, of course, later we had quantum mechanics come in and say, not so fast, not everything is so deterministic, and there's chance involved, back to probability by Pascal, as the core of the inner workings of the universe on a small quantum, physics level. There's probability kind of hardwired into the universe as far as we can tell, via quantum mechanics. So probability is not just a good way to win better at Las Vegas. It's a better way to understand how the universe actually works at the particle level. That's very, very fundamental. So here's his Principia Mathematica tome. This is actually his own personal copy. He actually made some corrections by hand. That'll probably fetch a pretty penny on eBay, right? He invented the reflecting telescope on top of everything else. The refracting telescope using lenses cannot be scaled up so much, because the lenses get bigger and bigger, and light cannot pass through all this glass. But if you have mirrors, a mirror can be arbitrarily large and still reflect light perfectly. So because of him, we have much better telescopes. The Hubble Space Telescope is based on the same principle, reflecting, not refracting, mirrors, not lenses. And so we owe, even stuff in astronomy to him. He discovered orbits. If you throw a ball far enough, it will not just fall farther away, it will eventually start to orbit, because the Earth's surface is round, and the Earth's surface starts to fall away via geometry from the falling object, and they do it in sync, and that's called an orbit. So space flight, again, is based on his principles. He also discovered the principle of inertia, the prism, and so on. Here's Newton's method for interpolating roots, one of my favorite cartoons right here. And if you're a Star Trek-y fan, there's there's an episode of Star Trek in the 80s, the New Generation, where they're sitting in the holodeck, and the 4 of them are playing poker, the 4 of them being Isaac Newton, Data, Einstein, and who's this guy in the wheelchair? Stephen Hawking. And he actually came on the set. That's really him. And it's kind of a funny episode. If you're geeky enough, go back and watch it. And Data is trying to explain to Newton the laws of poker, and Newton looks at him and says, "Don't patronize me, sir. I invented calculus, And there's some funny exchanges. Anyway, your mileage may vary, but I thought it was pretty cute. He appears on the British pound, and lots and lots of stamps feature him of almost every country in the world. These are just a few. As I was looking around for stamps featuring these people, Newton by far had the largest amount. That shows you the impact and the influence he had on everything and everybody in every single country acknowledges and appreciates it, and that's pretty cool. And some of these stamps feature his inventions, like the reflecting telescope and his theory of gravity. Some of them have actual equations on them. One of my favorite stamps that acknowledge Newton is is this series here. This is from Korea. It's not South Korea, by the way. This is North Korea. And North Korea, as you know, barely exists, barely even acknowledges that the rest of the world exists, and yet they acknowledge this Westerner, and that says a lot. It doesn't make up for the fact that they killed one of our students, but I digress again. So he gets a lot of homage from literally everybody and everywhere in the world for his contributions. We owe this guy a lot. Leonhard Euler basically invented graph theory. Famously, the bridges of Königsberg. There was a question of whether you can take an afternoon stroll and cross every bridge exactly once without retracing your steps, and nobody could solve that for centuries. And he came around and translated it into a so-called abstract graph where the land masses were nodes and the bridges were edges. And he proved a much more general theorem that you can do this so-called Euler tour for every single graph that has a degree of odd degree, nodes of odd degree at most, 2 nodes of odd degree, and hopefully none. Then you can do a tour. If you have 2 nodes of odd degree, you can do a path. That's the theorem, and this was a very special case of it. And that pioneered and founded the entire field of graph theory. And he gets to be on the Swiss franc before the euros. He wrote entire treatises in various areas. He has a so-called Euler formula and Euler equation. In Geneva, there's a whole museum dedicated to him. And when I've been there, I was quite delighted. It was a pretty fun museum tour to see all of his works. And one of my favorite posters has 5 of Euler's formulas here with certain variables highlighted, spelling Euler, right there. One of them, of course, is Euler's formula, which is said to be the most beautiful equation in all of mathematics, and quite unbelievable when you look at it. If you raise e to the pi I, you add 1, and you get 0, which is kind of amazing. So this equation involves all the famous 5 constants for mathematics, 0, 1, e, pi, and I, and all the arithmetic operations, right? Addition, multiplication, exponentiation, and equality. It's hard to come up with a formula that has, this kind of property and so simple and elegant and ubiquitous. Of course, a lot of analytic geometry is based on this formula and so on. So that's due to. He also appears in Simpsons episodes. If you watch carefully Simpsons episodes, they have mathematicians on staff whose job is to insert these little cute mathematical quirks and jokes and humor into the episodes, if you're quick enough to notice it. If not, it's still a fun episode, but if you watch these things, it's even cooler. So there's lots of books on graph theory, literally thousands of books, entire courses. They're everywhere, graphs. I'm just showing you, my favorite 60 books on graph theory, but there's many, many more. And there's entire conferences on graph theory. Again, I'm just showing you a few conferences on graph theory. These happen every single year, so it's a very blossoming, booming field. It's been like that for a couple of centuries. And there's entire journals on it. So here's some more conferences, international conferences on graph theory happening regularly. Here's one in Europe, right? And here's a journal on graph theory, another journal on graph theory. Now, why all this buzz about graphs? Well, because they appear everywhere, and they can model almost anything you can think of, right? So in GPS systems, they model paths, and Google Maps uses them, and your GPS system uses them on your iPhone or smartphone, where vertices model intersections and edges correspond to roads, and it finds the shortest paths based on Dijkstra's algorithm run over this graph representing the terrain and the streets and the intersections. Subway maps, same thing. Vertices represent stations, edges represent train tracks, and those can be very nicely modeled with graphs. Computer networks are modeled with graphs. Vertices are computers or routers. Edges are simply links, fiber, and using graphs you can model internets, networks, all sorts of local networks, global networks. The World Wide Web is one big graph where vertices are pages and edges are just links or URLs. Social networks like Facebook, the vertices are people and edges are friends relation between people, connecting people. So all of you are nodes in a big giant social, assuming you're on Facebook. I don't want to be presumptuous. I don't use Facebook much, but in social networks could be easily modeled as graphs very naturally, as can many other things. Databases, where vertices are records, edges are relations. Electrical grids, obviously, vertices are generating stations or transformers. Edges are cables, electric cables, wires. Integrated circuits. Vertices are transistors. The edges of these graphs are wires. So it just shows you the utility of graphs, and they're literally everywhere. In CADs of buildings, computer-aided design, blueprints, vertices are connectors and edges are ducts. Semantic nets, finite automata, the vertices are states, the edges are transitions. If you're in theory, how many are in my theory course, by the way? Okay, good. So wow, that's a lot. So don't worry, we're going to go into all this stuff in much greater detail, especially the things like finite automata and transitions and state sets and so on. So here you're getting almost like a commercial, like a short snapshot into what we're going to study, for the rest of the course in much greater detail and a much deeper dive, right? Time and space complexity classes, like a Chomsky hierarchy, which again we'll study in theory. Vertices are classes and edges are subsumption relations and so on. Map coloring, vertices are countries, edges are neighboring countries. And Erdős numbers, like the 6 degrees of separation. Bacon numbers, edges are people. Vertices are people, and the edges are either co-authors, or in the case of Kevin Bacon, co-stars in the movie. How many heard of the oracle of Bacon, the 6 degrees of separation? Kevin Bacon numbers. Okay, so it was actually invented here at UVA 20 years ago in the 90s by a couple of our graduate students who probably had a little bit too much free time on their hands, and. At first Kevin Bacon was really upset at this. He thought he was being made fun of, which he kind of was actually. But then he realized that any PR is good PR, and then he came to embrace it and love it. And now he brags about it in interviews. So brings us to Carl Friedrich Gauss, the so-called Prince of Mathematics. Basically pioneered modern number theory. The Greeks already did some number theory, Diophantine equations, but they was kind of primitive and they didn't know a whole lot, and Carl Friedrich Gauss kind of raised it to the next level. Many things are named after him. Gaussian distribution, like normal bell-shaped curves, that's after him. Gaussian elimination, a lot of matrix algebra, linear algebra. Gaussian noise, white noise, named after him. Degaussing, right? Demagnetizing or magnetizing, and the standard international unit of magnetic field strength is the Gauss, spelled with a small letter, G. And some of his students themselves were quite illustrious mathematicians who did a lot of interesting math. On the German Marx, he appears, again, before the euro, which wasn't that long ago, and the bell-shaped curve, including the actual equation of the distribution, is on the money, which is quite impressive when you see non-trivial mathematical equations and formulas and identities on the bills in your pocket. That's, it gives you some respect for the people who actually decided to do that, as opposed to just have some ancient politician that was particularly impactful or memorable. So that's Gauss. And then Hamilton generalized numbers to much more general concepts. So he basically invented quaternions, which are a generalization of the complex numbers. And quaternions are non-associative, but they're very, very useful in computer graphics and many other fields. So his work on quaternions basically directly relates to computer graphics and computer science in general. And that's a map of the multiplication table multiplication of quaternions. We have I, J, and K, and they're all square root of -1, but they're not the same as each other, I being one of them, but J and K are other two imaginary quantities separate from I, and that gives you a whole new robust way to do certain types of math, and that's quite used in physics and quantum mechanics. And that was generalized later to octonions that have 8 quantities, not just 4. And later, that was further generalized into sedentions that have 16, and in theory class we'll go a little bit deeper into these things. So that generalized numbers, we all know the prime numbers, which are a subset of the natural numbers, which in turn are a subset of the integers, which in turn are a subset of the rational numbers, quotients, and then those are subsets of the reals, like square root of 2, algebraic numbers, and then you get transcendental numbers like pi and e, and the golden ratio, and then those are all the real numbers. And then, of course, you all know about a plus bi, where a and b are real, but I is the imaginary square root of -1. And that's where usually people's knowledge stop or get stifled. And Hamilton added the quaternions outside the complexes. Then the octonions, the sedentians were added after that. These are called hypernumbers sometimes. And then surreal numbers. In theory, we'll go a little bit more into surreal numbers. You can do some extra credit readings about them. But they generalize the reals because they also contain infinitesimal quantities and infinite quantities as well as finite quantities, which is quite phenomenal. And then you have even bigger generalizations of the circumplex numbers. Numbers of the form a plus bi, where I is still the square root of -1, but a and b are no longer just real, they're surreal. And this is not a joke. It's technical definitions to all these things, and Knuth wrote a nice little novella about surreal numbers, which I urge you to read in the theory class for fun and profit. And then, of course, there's more stuff beyond that. But Hamilton gets credit for kind of opening our eyes to these larger sets of more generalized numbers rather than sticking with just the reals and the complexes. Don't get me wrong, using reals and complexes, you can get pretty far. But when you have these other numbers kicking in, you can do a lot more. Like I already mentioned, quaternions are essential in computer graphics. It's not just some abstraction that is a mathematical exercise. It's quite practical. And in the theory course, we'll prove some theorems of this form, that some real numbers are not finitely describable, and some finitely describable numbers are not even computable, and so on and so on. More later about that in the theory course. George Boole, 1800s, basically said, folks, we can do some pretty interesting stuff just with two numbers, not an infinity of numbers, just 0 and 1. That's it. And at the time, it sounded kind of ludicrous. It sounded pretty vacuous or ineffectual. But he's the father of Boolean logic. That's why we call it Boolean logic, because it's named after him, George Boole. And based on that premise that 0 and 1 suffice to do any arithmetic or algebra or any kind of math for that matter, in fact, not just any science for that matter, that was so novel that it basically kind of opened the floodgates for designing computers. And today, all of our computers are based on Boolean logic and binary number systems, zeros and ones. We could design computers that use the decimal number systems or hexadecimal or any other number system. They would be equivalent. But 0 and 1 have this nice property that, well, you tell me, what's the advantage of using only zeros and ones in a computer? Why don't we have 10 different values of voltage or current, or why just stick to 2? Yeah. On and off. What's the advantage of having just an on and an off and no other state? Why not have like a lukewarm on and a strong on and a really strong on and a couple of other versions of off? We could do that electrically. Think about it. Yeah. Safer? Why safer? Less errors. It's fault tolerant. Dealing with zeros and ones is fault tolerant, because the minute you deviate a little bit away from the 1, you know that you're not all the way to 0, because it's just like 0.9 instead of 1, or 0.2 instead of 0. So if you have any kind of fluctuations in voltage or current or temperature or in resistance or capacitance or whatever it is the measurements are, you know automatically how to correct that error. So you're much more fault tolerant if you just have 2 extreme values as opposed to 20 values in between. So it's about fault tolerance. Think about it. If not for that, computers would be a lot more glitchy and harder to design and harder to recover from all sorts of errors that occur all the time. Right? So he was one of the founders of computer science. And there's even a class of humor called Boolean humor. This says dad or mom in binary. And anyway, your mileage may vary, but De Morgan, one of his contemporaries, took that notion of Boolean logic and created a whole logic around it, a whole system of reasoning around it. Predicate logic and predicate calculus and De Morgan's law, the relation algebra. So he kind of took Boole's ideas and kind of ran with it. And all symbolic logic that we know today was pioneered by him at the time. And again, that was, and still is, the basis of computation and programming and formal methods and anything we design, that has these kind of components in it, transistors and logic components to it. So Babbage, around the 1800s, early 1800s, designed a mechanical computer. And he was one of the fathers of computing. Computing has many parents. And his computer was mechanical. Remember, electricity wasn't discovered yet. This was early 1800s, 1820s. And so his computer was programmable, amazingly, even though it was completely mechanical. You had to turn a big crank to get it to work. It was full of gears and levers like a big Swiss watch. Here's one of the registers from this computer. And it uses paper tape, punch tape, to actually interpret the program. So it wasn't just a big mindless crank. It could actually be programmed using this paper tape. And it was the world's first general mechanical computer. Remember, the Antikythera by the Greeks was also a mechanical computer, but it was small and specialized. It could do ellipses and measure planetary orbits and so on. But that's about it. You couldn't generally program it to do other things. This one you could. It had 25,000 parts, weighed 15 tons, had 31 digits of precision. That's pretty good for the 1820s. Used a decimal number system, a big crank. Here you see the big crank. Took quite a lot of power to make this thing go forward. Here are some parts. Here are some animations of how it worked. Basically like a big Swiss watch with lots of springs and gears and levers and cams. And you can construct it of other devices, not just the way he did it, but here's a Meccano. Here's a Lego version of the analytical engine, right? It's the world's first general purpose computer. Then later he designed the analytical engine. This one he didn't completely finish building because it had even more parts and more expensive, but it had a fully programmable CPU. It had microcode. It had loops, and even had a printer. This is 1830s. This is before electricity was invented, and he was designing a printer for a general computer. And you could multiply two 20-digit numbers in 3 minutes. Today, it doesn't sound like much, because in 3 minutes, your computer can literally do a trillion things, not just 2. But at the time, it was fast, orders of magnitude faster than humans, and certainly a lot more precise than humans can muster. And his blueprints for it, we only built certain parts of it, but not the whole thing. Later, pretty recently in the 90s, we actually used these blueprints to construct larger parts of the whole thing, and it worked exactly the way he prescribed in his blueprints. There were no errors in the blueprints, which is kind of amazing. He was very, very meticulous, very, very precise. Here are some other pieces of reconstruction of his mechanical engines. And here's the mechanical printer that he designed. Why would you need a printer even? Like, what's the thing with a printer? Somebody say something. If you don't have a printer, what's going to happen? You can't see the results. Remember, this is 1820s, 1830s. There's no disk drives to record things on. There's no screens to watch. It would just crank and crank and crank, and as it cranked more, the old results cranked out would be cranked over, and then nobody would see them, nobody would record them. So you'd have a printer to kind of keep record of certain intermediate points in the computation, so that you can sort of see what happened up until that point. Otherwise, you'd lose it. So there's entire institutes devoted to his work, and that brings the Countess Ada Lovelace, right, his contemporary. She worked with him, and she wrote the first manual for this world's first computer. And DoD language Ada, the mil-spec Ada language, is named after her. She gets a lot of credit for doing this, especially for a woman to do that in those days. It was almost unheard of. But she dived in and she wrote the first programming manual and the first programs for his analytical engine. And there's even an award after her given every year in her honor. Tim Berners-Lee, the inventor of the internet, got the award a few years ago. Here's her programming first program. So this is history's first program written by her for his analytical engine. So she gets the honor of being the world's first programmer. And she also anticipated that computers would be very general, be able to do arbitrarily complex things, which at the time was not obvious at all. And I'm quoting a few things of hers from her paper. Her paper was several times longer than the description of the actual computer that she wrote about, and she anticipated the many, many uses of computers down the line. So she gets a lot of credit for that. So with that, we'll stop. We'll continue next time and get all the way up to Turing and hopefully beyond, and we'll see you then.
Please remember to put your worksheets on the front bench on your way out. Thanks.